In 1967, Jocelyn Bell Burnell was a graduate student at Cambridge University. She was helping to build a massive radio telescope. It covered an area the size of 57 tennis courts. Its job was to scan the sky for quasars, distant and incredibly bright objects. One day, she noticed a strange signal in the data. It was a pulse of radio waves. It came and went with perfect regularity. The pulse appeared every 1.337 seconds. It was so precise, it was a better timekeeper than any clock on Earth. At first, the team couldn't explain it. The signal was too fast and too regular to be from any known celestial object. For a while, they half-jokingly labeled the source LGM-1. It stood for Little Green Men. It seemed more plausible than any natural explanation they could think of. But then Bell Burnell found another signal from a different part of the sky with its own perfect rhythm. Then a third and a fourth. This wasn't a message, it was a new kind of star. They had discovered pulsars. A pulsar is a neutron star. It is the collapsed core of a giant star that has exploded. It has more mass than our sun crushed into a ball just a few miles across. It spins hundreds of times per second. And the physics that describes this incredible object, this lighthouse in the cosmos, comes directly from Albert Einstein's theory of relativity. Einstein published his ideas more than 50 years before Bell Burnell saw that strange pulse. He could never have imagined an object so extreme, yet his equations described it perfectly. And that's the story of relativity. It's a theory from the past that keeps predicting the future. It continues to describe the universe in ways that we are still just beginning to understand. You know, it's not just a historical idea, it's a live tool still revealing new and strange things about the world we live in. Number 21, gravity is not a force. An astronaut in orbit feels no gravity. They are weightless. Yet the Earth's gravity is what holds them in orbit. It is still about 90% as strong up there as it is on the surface. If you drop an apple on Earth, it falls. If an astronaut on the International Space Station lets go of an apple, it floats. But both the apple on Earth and the astronaut with their apple are following the exact same rule. They are both taking the straightest possible path through space-time. This is the core idea of general relativity. And Einstein's biggest leap was to say that gravity is not a force pulling things. Instead, gravity is the shape of the universe. Massive objects like planets and stars warp the fabric of space-time around them. Think of it like a heavy bowling ball placed on a stretched out rubber sheet. The ball creates a dip, a curve in the sheet. Now, if you roll a small marble nearby, it doesn't go in a straight line. It follows the curve created by the bowling ball. The marble is not being pulled by the ball. It is simply following the straightest path it can on a curved surface. That's what's happening with Earth and the Sun. The Sun is the bowling ball. Earth is the marble. We are not being pulled by the Sun's gravity. We are following a straight line through the curved space-time created by the Sun's mass. This straight line in curved space-time is called a geodesic. An orbit is a geodesic. The path a falling apple takes is a geodesic. The path the weightless astronaut takes is also a geodesic. The astronaut feels no force, because no force is acting on them. They are in free fall, just like the apple. The only reason we feel a force on Earth is because the ground gets in the way. The ground pushes up on our feet, stopping us from following our natural, straight path through curved spacetime. That upward push is what we feel as weight. This completely changed physics. Before Einstein, space was just an empty stage where things happened. Time was just a clock ticking in the background, but Einstein showed that space and time are connected. They form a single, dynamic entity called spacetime. And this entity is not a passive background. It is an active participant. Matter tells space-time how to curve, and the curve of space-time tells matter how to move. This is a radical departure from the old idea of an invisible force reaching out across empty space. It explains why gravity affects everything, including light, which has no mass. Light isn't being pulled by gravity. The light is simply following the straightest possible path through the curved universe. This one idea, that gravity is geometry, underpins almost every major discovery in cosmology for the last century. It's the reason we can talk about black holes, the Big Bang, and the expansion of the universe. It all starts here, with the realization that the feeling of being pulled down is just an illusion. Number 20, Relativity solved the mystery of a rogue planet. For more than 50 years, the planet Mercury was a problem. Its orbit didn't make sense. According to Isaac Newton's law of universal gravitation, planets should trace a perfect ellipse around the sun. This ellipse should stay fixed in space, but Mercury's didn't. Its elliptical path was slowly rotating. The point of its closest approach to the sun, called the perihelion, was shifting forward with each orbit. The shift was tiny. It was only about 574 arcseconds per century. An arcsecond is 1/3600th of a degree. So this was a very small wobble. Astronomers in the 19th century were very good at calculations. They accounted for the gravitational tugs of all the other planets, like Venus, Earth, and Jupiter. These calculations explained most of the shift. They accounted for 531 arcseconds of the wobble. But there was a discrepancy. There were 43 arcseconds per century that nobody could explain. This was a huge crisis for physics. Newton's laws had worked perfectly for everything else in the solar system. They had even been used to predict the existence of Neptune before it was ever seen. But they failed at Mercury. To solve the problem, astronomers proposed a new planet. They suggested there was a planet orbiting even closer to the sun than Mercury. They called it Vulcan. Its gravity, they reasoned, would be tugging on Mercury and causing the strange wobble in its orbit. For decades, astronomers searched for Vulcan. People claimed to have seen it. They made observations during solar eclipses. But it was never found. The planet didn't exist. The problem wasn't a missing piece of the solar system. The problem was the theory of gravity itself. Then, in November 1915, Albert Einstein applied his new theory of general relativity to the problem. In his theory, gravity was not a force, but a curvature of spacetime. The sun, being massive, creates a deep curve in spacetime. Mercury, being the closest planet, orbits deep inside this gravity well. Einstein's equations predicted that this deep curve would cause the planet's orbit to precess, or wobble, exactly as observed. When he did the math, the numbers came out perfectly. General relativity predicted an extra shift of 43 arcseconds per century. It was the exact amount that had been missing. Einstein later said that his heart trembled with excitement when he saw the result. He was so excited he had palpitations. This was the first major confirmation of his theory. It wasn't just an abstract mathematical idea. It could solve a real, long-standing problem in astronomy that the best theory of the last 200 years could not. It explained the motion of Mercury without any need for a phantom planet. It showed that Newton's laws were not wrong, but incomplete. They were a very good approximation for places with weak gravity, like Earth's orbit. But in the strong gravitational field close to the sun, you needed a new set of rules. And Einstein had found them. The ghost planet Vulcan vanished, and a new understanding of the universe took its place. Number 19, the Earth twists reality around itself as it spins. The Earth is not just sitting in space-time. It is spinning, and that spin does something very strange. It drags the fabric of space-time around with it. This is not a metaphor. The space and time around our planet are literally being twisted by its rotation. This effect is called frame dragging, or the Lenz-Thirring effect. It was predicted by Austrian physicists Josef Lenz and Hans Thirring in 1918 using Einstein's equations. But the effect is incredibly small. It is so small that Einstein himself thought it would be impossible to ever measure. For decades, frame dragging was just a theoretical curiosity, but in 2004, NASA launched a mission to test it. The mission was called Gravity Probe B. It was one of the most technologically sophisticated experiments ever attempted. The probe carried 4 of the most perfect spheres ever created by humans. They were made of fused quartz and silicon about the size of a ping pong ball. They were so perfectly round that if you scaled one up to the size of the Earth, the tallest mountain would be only 8 feet high. These spheres were cooled to near absolute zero and set spinning at thousands of revolutions per minute inside the probe. They were gyroscopes. The idea was simple. According to Newton's physics, a gyroscope pointing at a distant star should stay pointing at that star forever. It should not drift. But according to Einstein's relativity, 2 things should happen. First, the simple curvature of spacetime around Earth, the effect of gravity, should cause the gyroscopes to drift slightly. This is called the geodetic effect. Second, the twisting of spacetime by Earth's rotation frame dragging should cause another, much smaller drift in a different direction. The probe orbited the Earth over the poles for more than a year. Its gyroscopes pointed at a guide star called IM Pegasi. The scientists needed to measure a change in the gyroscope's orientation that was almost unimaginably small. The predicted drift from frame dragging was just 39 milliarcseconds over a year. A milliarcsecond is 1,000th of an arcsecond. It's the width of a human hair seen from 10 miles away. The mission was incredibly difficult. The probe had to be shielded from magnetic fields, solar winds, and even the tiny pressure of sunlight. After collecting the data, it took the science team 5 more years of careful analysis to get the final results. In 2011, they made the announcement. They had measured the geodetic effect to within 0.28% of the predicted value. And they had measured frame dragging. The gyroscopes had been dragged along by the twisting space-time around Earth. The measurement matched Einstein's prediction to within about 19%. Einstein was right again. The Earth really does twist reality. This means that if you were to draw a perfectly straight line in space near Earth, it would be slightly bent by this twisting. It's a profound idea. Space-time is not a rigid backdrop. It is a fluid-like medium that can be stirred and swirled by the objects moving through it. Number 18, gravity makes light tired. Or light from a star has to travel a long way to reach us. If that star is massive, its light has to climb out of a deep gravity well to escape. This climb takes energy, and as light loses energy, its wavelength gets longer. It shifts towards the red end of the spectrum. This is called gravitational redshift. It's a direct consequence of general relativity. It's not the same as the more famous redshift caused by the expansion of the universe. This is a local effect caused by gravity itself. Einstein predicted this effect in 1911, even before he had the full theory of general relativity. His logic was based on the equivalence principle. This principle states that the effects of gravity are indistinguishable from the effects of acceleration. If you are in a sealed room on Earth, you feel the pull of gravity. If you are in a sealed rocket in deep space accelerating upwards at 9.8 meters per second squared, you will feel the exact same sensation. You couldn't tell the difference. So consider a light beam sent from the floor of the accelerating rocket to the ceiling. By the time the light reaches the ceiling, the rocket has picked up speed. The ceiling is moving away from where the light was emitted faster than the floor was. This causes a Doppler shift, making the light appear redder to an observer at the ceiling. Because of the equivalence principle, the same thing must happen in a gravitational field. This light sent from a lower altitude to a higher altitude must lose energy and become redshifted. Gravity saps its strength. This was a bizarre prediction. For a long time, it was difficult to measure. The effect is very small for objects like the Earth or the Sun. The first successful measurement on Earth was the Pound-Rebka experiment in 1959. They used a tower at Harvard University that was only 22.5 meters tall. They shot gamma rays from the bottom of the tower to a detector at the top. Gamma rays are a form of light with a very specific known wavelength. The experiment had to be incredibly precise to detect the tiny shift in wavelength caused by Earth's gravity over just 22.5 meters. But they did it. They found that the gamma rays arriving at the top of the tower had a slightly longer wavelength than when they started. They had been redshifted, just as Einstein predicted. Today, gravitational redshift is a routinely measured phenomenon. We see it in the light from white dwarf stars and neutron stars, which have very strong gravitational fields. The effect is also crucial for the functioning of the Global Positioning System (GPS). The clocks on GPS satellites are in a weaker gravitational field than clocks on Earth. This means they tick faster. Gravitational redshift is essentially the same phenomenon as gravitational time dilation, just looked at from the perspective of light. The light wave's frequency is its clock. As it climbs out of a gravity well, its frequency drops, and its clock slows down. So the light becomes redder. This shows a deep connection between gravity, time, and the nature of light itself. A beam of light is a clock, and gravity changes the rate at which that clock ticks. Number 17, Massive Objects act like lenses for the universe. In 1919, a British astronomer named Arthur Eddington led 2 expeditions. One went to the island of Principe off the coast of Africa. The other went to Sobral in Brazil. Their goal was to watch a total solar eclipse. But they weren't interested in the sun's corona. They were there to test Albert Einstein's new theory of general relativity. One of the theory's most dramatic predictions was that gravity bends light. Einstein's theory said that the immense gravity of the sun should bend the path of starlight passing near it. This bending would make the stars appear to be in a slightly different position in the sky than they actually were. Normally, you can't see stars near the sun because the sun is too bright, but during a total solar eclipse, the moon blocks the sun's light and the stars become visible. Eddington's teams planned to take photographs of the stars near the eclipsed sun. They would then compare these photos to photos of the same star field taken 6 months earlier when the sun was in a different part of the sky. The experiment was a success. The measurements were difficult and the data was noisy, but the results were clear. The stars' positions had shifted, and the amount of the shift matched the prediction of general relativity. It was double the amount that would have been predicted by Newtonian physics. The news made Einstein an international celebrity overnight. The London Times headline read, "Revolution in Science New Theory of the Universe, Newtonian Ideas Overthrown." This effect is now called gravitational lensing. It's not just a subtle shift in a star's position. It has become one of the most powerful tools in modern astronomy. Any massive object like a galaxy or a cluster of galaxies can act as a lens. It bends the space-time around it, and this curved space-time deflects the light from objects behind it. If the alignment is just right, the lens can magnify and distort the image of the distant object. Sometimes it can create multiple images of the same object. A distant quasar might appear as 2 or 4 distinct points of light arranged around the lensing galaxy. One of the most famous examples is the Einstein cross, where the gravity of a foreground galaxy splits the light from a background quasar into 4 separate images. In other cases, if the alignment is perfect, the light can be smeared into a ring called an Einstein ring. These cosmic lenses allow astronomers to see things that would otherwise be too faint or too far away. They can study the first galaxies that formed in the early universe. By analyzing the distortions in the lensed images, they can also map the distribution of mass in the lensing object. This is how astronomers first found convincing evidence for dark matter. They observed that galaxy clusters were bending light far more than could be explained by the visible matter, the stars and gas alone. There had to be a huge amount of invisible mass creating the extra gravity. Gravitational lensing allows us to see this dark matter by its gravitational effects. What started as a subtle test of a new theory has become a way to weigh the universe and discover its hidden components. Number 16, the universe is getting bigger every second. When Einstein first developed the equations of general relativity in 1915, they gave him a surprising result. They predicted that the universe could not be static. It had to be either expanding or contracting. At the time, the prevailing view among scientists was that the universe was eternal and unchanging. It was static. This result bothered Einstein. He thought his equations must be wrong. So he added a new term to them, a kind of cosmic anti-gravity force. He called it the cosmological constant. He tweaked its value so that it would exactly balance the pull of gravity, allowing for a static universe. But other scientists took the original equations more seriously. In the 1920s, a Russian mathematician named Alexander Friedmann and a Belgian priest and physicist named Georges Lemaître independently worked through Einstein's equations. They both concluded that the equations predicted an expanding universe. Lemaître went further. He reasoned that if the universe is expanding now, it must have been smaller in the past. If you run the clock backwards far enough, everything in the universe must have been crushed together into a single point, a primeval atom, which then exploded. This was the first articulation of what would later be called the Big Bang Theory. At the time, there was no evidence for this. It was just a mathematical possibility. But then, in 1929, the American astronomer Edwin Hubble made a landmark discovery. He was observing distant galaxies from the Mount Wilson Observatory in California. He measured their distances and also their velocities. He found that almost all galaxies are moving away from us. And he found a clear relationship. The farther away a galaxy is, the faster it is moving away. This is exactly what you would expect to see in an expanding universe. Imagine baking a raisin cake. As the cake batter rises, all the raisins move away from each other. A raisin close to you moves away slowly. A raisin on the other side of the cake moves away much faster. From the perspective of any single raisin, all the other raisins are receding. Hubble's observation was the first proof that the universe was not static, it was expanding. Einstein later visited Hubble at Mount Wilson and looked through the telescope himself. He admitted that adding the cosmological constant to his equations was his biggest blunder. His original theory had been trying to tell him something profound about the universe, but he hadn't listened. The expansion of the universe is not like an explosion of galaxies into empty space. It's the expansion of space itself. The galaxies are not flying through space. They are being carried along by the expanding fabric of spacetime. This discovery completely changed our understanding of the cosmos. It gave us a history for the universe. It implied a beginning, the Big Bang, which is now the cornerstone of modern cosmology. And it all came from taking Einstein's equations at face value. Number 15, Einstein's biggest blunder might be his greatest triumph. In Einstein, called the cosmological constant, his biggest blunder, he introduced it in 1917 to force his equations to describe a static universe, which was the common belief at the time. When Edwin Hubble discovered in 1929 that the universe was actually expanding, the cosmological constant seemed unnecessary. Einstein happily discarded it. For most of the 20th century, it was treated as a historical footnote, an interesting mistake by a great mind. Most physicists assumed its true value was zero, but the story didn't end there. In 1998, two independent teams of astronomers were working on a project to measure the expansion rate of the universe more precisely. They were using type Ia supernovae as standard candles. These are exploding stars that all have roughly the same intrinsic brightness. By measuring how faint they appear, astronomers can calculate how far away they are. By measuring their redshift, they can calculate how fast they are moving away from us. The plan was to look at very distant supernovae to see how the expansion of the universe had changed over time. Everyone expected to find that the expansion was slowing down. Gravity pulls everything together. The mutual gravitational attraction of all the galaxies should be acting as a brake on the expansion. The only question was how much it was slowing down, but both teams found the exact opposite. The very distant supernovae were fainter than they should have been. This meant they were farther away than expected. The only way to explain this was if the expansion of the universe was not slowing down. It was speeding up. The universe is accelerating. This was a shocking discovery. It turned cosmology on its head. It meant there must be some kind of mysterious energy pushing space-time apart, overwhelming the pull of gravity on cosmic scales. Scientists didn't know what it was, so they gave it a name, dark energy, and the simplest mathematical way to represent this dark energy in the equations of general relativity is to use. It turns out that Einstein's blunder might actually be a profound insight into the nature of the universe. The cosmological constant can be interpreted as the energy of empty space itself, the energy of the vacuum. This vacuum energy would have a strange property. It would exert a negative pressure, an outward push that would cause space to expand. According to current measurements, this dark energy makes up about 70% of the total energy density of the universe. Or dark matter makes up about 25%. The normal matter that we are made of, the stuff of stars and galaxies and people, is less than 5% of the total. We still don't know what dark energy is. The value of the cosmological constant predicted by our best theories of particle physics is wildly different from the value we observe. It's off by a staggering 120 orders of magnitude. This is one of the biggest unsolved problems in physics. But the evidence for its existence is strong, and it brings Einstein's story full circle. The term he invented to fix a problem that didn't exist has returned as the best description we have for the biggest mystery in the cosmos. His blunder has become a new frontier of science. Number 14, the universe is filled with the sound of space-time ringing. In September 2015, two giant detectors, one in Livingston, Louisiana, and the other in Hanford, Washington, picked up a faint signal. The signal lasted for less than half a second. It started as a low rumble and quickly rose in frequency and intensity. It was a chirp. That tiny chirp was the sound of one of the most violent events in the universe, the collision of two black holes. The event happened 1.3 billion years ago. The two black holes, one about 29 times the mass of the Sun, and the other about 36 times, had been spiraling around each other. As they got closer, they spun faster and faster until they were moving at nearly the speed of light. Then they merged. In the final fraction of a second, the merger converted 3 times the mass of the Sun directly into energy. But this was not energy in the form of light or heat. It was energy in the form of gravitational waves. These are ripples in the fabric of space-time itself. Einstein's general theory of relativity predicted their existence in 1916. He showed that accelerating massive objects should create disturbances in space-time that travel outwards at the speed of light. But he also thought these waves would be so incredibly weak that they would never be detected. For a century, gravitational waves were a ghost. We had indirect evidence for them. In the 1970s, astronomers Russell Hulse and Joseph Taylor Jr. discovered a binary pulsar, 2 neutron stars orbiting each other. They found that the orbit was slowly shrinking. The 2 stars were losing energy and spiraling closer together. The rate at which they were losing energy perfectly matched the rate predicted by general relativity if they were emitting gravitational waves. This earned Hulse and Taylor the Nobel Prize in Physics in 1993. But it was still not a direct detection. Directly detecting these waves required an instrument of unbelievable sensitivity. That instrument is LIGO, the Laser Interferometer Gravitational Wave Observatory. Each LIGO detector consists of 2 4-kilometer-long vacuum tunnels arranged in an L shape. A laser beam is split and sent down each arm. The beams bounce off mirrors at the ends and return to the starting point. Normally, the 2 returning beams are set up to cancel each other out perfectly. But if a gravitational wave passes through, it will stretch one arm of the detector while squeezing the other. This tiny change in the arm's lengths, far smaller than the width of a proton, will cause the laser beams to no longer cancel out. A flicker of light will be detected. The chirp detected in 2015 was the first time this had ever happened. It was a direct detection of a gravitational wave. It was a new way of observing the universe. For all of human history, we have studied the cosmos using light in all its forms, from radio waves to gamma rays. But gravitational waves are not light. They are vibrations of space-time. They travel through the universe almost completely unimpeded. They carry information from events that we could never see, like the merger of two black holes, which produces no light. Since 2015, LIGO and its partner Observatory Virgo in Italy have detected dozens of these events. They have seen black holes merging, they have seen neutron stars colliding, an event that produces both gravitational waves and a flash of light. This new field of gravitational wave astronomy is allowing us to listen to the cosmic symphony. We are hearing the universe for the first time. Number 13, there are places where time itself comes to a stop. Just a few months after Einstein published his theory of general relativity, a German physicist named Karl Schwarzschild found the first exact solution to its complex equations. He was serving on the Russian front during World War I at the time. His solution described the space-time around a single spherical, non-rotating mass like a star or a planet. But his solution contained a strange feature. It predicted that if you could compress a mass into a small enough volume, the curvature of space-time around it would become so extreme that nothing, not even light, could escape. The boundary of this region of no escape is called the event horizon. The radius of this sphere is now called the Schwarzschild radius. For an object with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. For the Earth, it's about the size of a marble. If you could crush the Sun down to a ball 3 kilometers across, it would become a black hole. At the time, this was considered a mathematical oddity, not a real physical object. Einstein himself was skeptical that such a thing could form in nature. For decades, the idea remained in the realm of theory. But as our understanding of stellar evolution grew, scientists realized that black holes were an inevitable consequence of general relativity. When a very massive star runs out of fuel, it can no longer support its own weight. Its core collapses under its own immense gravity. If the core is massive enough, more than about 3 times the mass of the Sun, no known force in nature can stop the collapse. It will continue to shrink until it forms a black hole. General relativity makes some truly bizarre predictions about what happens near a black hole. One is extreme gravitational time dilation. To an observer far away, a clock falling towards a black hole would appear to tick slower and slower as it approached the event horizon. In fact, it would seem to take an infinite amount of time to actually reach the horizon. The clock would appear to freeze in time at the edge of the black hole, its light getting redder and dimmer until it faded away completely. From the perspective of the clock itself, however, time would pass normally. It would cross the event horizon in a finite amount of time. Once inside the event horizon, all paths lead to the center. Space-time is so warped that the future direction for any object is always towards the singularity. The singularity is the point at the center of the black hole where the theory predicts that the density and curvature of space-time become infinite. Our current laws of physics, including general relativity, break down at a singularity. We don't know what happens there. For a long time, black holes were theoretical. But today, we have overwhelming evidence that they are real. We have detected the gravitational waves from merging black holes. We have observed stars orbiting a supermassive black hole at the center of our own Milky Way galaxy. And in 2019, the Event Horizon Telescope project released the first ever direct image of a black hole shadow, a dark circle silhouetted against the glowing hot gas swirling around it. These objects, once a strange solution on a piece of paper, are a fundamental part of our universe. Number 12, the theory breaks down at the most important moments. General relativity is an incredibly successful theory. It has passed every experimental test we've thrown at it. It describes the universe on the largest scales with stunning accuracy, but it has a problem. It has 2 blind spots. The theory breaks down in 2 very important places at the center of a black hole and at the very beginning of the universe. In both of these places, the theory predicts a singularity. A singularity is a point where the equations of general relativity go haywire. Physical quantities like density and spacetime curvature become infinite. This is not a description of a real physical thing. Infinity is a mathematical concept, not a physical one. When a theory predicts infinity, it's a sign that the theory is no longer applicable. It has stepped outside its domain of validity. It's a way for the theory to tell us, I don't know what happens here. At the center of a black hole, general relativity says that all the mass that fell into it is crushed into a point of zero volume and infinite density. This is the singularity. At the beginning of the universe, the Big Bang theory, which is based on general relativity, tells us that everything started from a singularity. All the matter and energy of the observable universe was concentrated in a point of infinite temperature and density. The problem is that these are the most extreme environments in the universe. To understand what really happens there, we need a theory that can handle both gravity and the physics of the very small. We need a theory of quantum gravity. General relativity is a classical theory. It doesn't include the principles of quantum mechanics, which govern the world of atoms and subatomic particles. Or quantum mechanics is our other great theory of the 20th century. It is also incredibly successful. But the two theories are fundamentally incompatible. They are written in different mathematical languages and are based on different principles. General relativity describes a smooth, continuous spacetime. Quantum mechanics describes a world that is fuzzy, probabilistic, and quantized, meaning it comes in discrete packets. Trying to combine them is the biggest challenge in fundamental physics today. Scientists have been working on it for decades. There are several promising approaches, like string theory and loop quantum gravity. These theories attempt to describe gravity in a quantum mechanical way. In these theories, there are no singularities. For example, some theories suggest that the singularity at the center of a black hole is replaced by a tiny, incredibly dense ball of something called quantum foam. Others suggest that the Big Bang was not a beginning from nothing, but a big bounce, where a previous contracting universe reached a minimum size and then rebounded into our own expanding universe. These are still speculative ideas. We don't have a complete and confirmed theory of quantum gravity yet, but the existence of singularities in general relativity is what tells us that we must keep searching for one. Einstein's theory is not the final word. It is a powerful and beautiful signpost pointing the way towards an even deeper understanding of reality. Number 11. The universe might have tunnels. The equations of general relativity are complex. They allow for some very strange and exotic solutions. One of the most famous of these is the Einstein-Rosen bridge, more commonly known as a wormhole. In 1935, Albert Einstein and his colleague Nathan Rosen were exploring the mathematics of black holes. They found a solution that connected a black hole to a white hole. A white hole is the theoretical time reversal of a black hole. While nothing can escape from a black hole, nothing can enter a white hole. Things can only come out of it. The connection between the two was a kind of tunnel or throat through spacetime. This was the first theoretical description of a wormhole. It's a hypothetical shortcut through spacetime. Imagine spacetime is a large sheet of paper. To get from one point on the paper to another, you would normally have to travel across the surface. But if you could bend the paper and punch a hole through it, you could create a much shorter path. A wormhole would be a three-dimensional version of that hole connecting two distant points in space or even two different points in time. The original Einstein-Rosen bridge is not a practical way to travel. It turns out that it's not traversable. The throat of the wormhole pinches off so quickly that nothing, not even a beam of light, would have time to get through it. It would collapse into a singularity. For a long time, wormholes were seen as just another mathematical curiosity, like black holes were at first. But in the 1980s, physicist Kip Thorne and his colleagues investigated whether a traversable wormhole could exist. They found that it might be possible, but it would require some very special conditions. To keep the throat of the wormhole open, you would need to prop it up with some kind of exotic matter. This is not normal matter. It would have to have negative energy density and a large negative pressure. In other words, it would have to be stuff that has anti-gravity properties. It would weigh less than nothing. We have never observed any matter with these properties. Quantum mechanics does allow for tiny fleeting fluctuations of negative energy in a vacuum, but we don't know if it's possible to gather enough of it to stabilize a wormhole. So, at the moment, traversable wormholes remain firmly in the realm of science fiction. There is no evidence that they exist in the real universe. However, their theoretical possibility is still a fascinating consequence of general relativity. It suggests that the structure of spacetime could be far more complex than we imagine. It could be filled with a quantum foam of tiny, constantly forming and disappearing wormholes at the smallest scales. The study of wormholes, even if they are not real, forces physicists to push the boundaries of general relativity and quantum mechanics. It makes them ask fundamental questions about the nature of space, time, and causality. Could you use a wormhole to travel back in time and create a paradox? What are the rules for a universe that contains such objects? These are the kinds of questions that arise when you follow Einstein's equations to their most extreme and logical conclusions. Number 10. The universe has a shape. What is the overall shape of the universe? Is it flat, like a sheet of paper? Is it curved like the surface of a sphere? Or is it curved like a saddle? This is one of the biggest questions in cosmology. And the framework for answering it comes from general relativity. According to Einstein's theory, the geometry of the universe is determined by its overall density of matter and energy. There are three basic possibilities. If the density of the universe is above a certain critical value, then there is enough matter and energy for gravity to eventually halt the expansion and cause the universe to collapse back on itself in a big crunch. In this case, space-time would have a positive curvature like the surface of a sphere. This is called a closed universe. If you were to travel in a straight line in a closed universe, you would eventually end up back where you started. It is finite in size, but it has no edge. If the density of the universe is below the critical value, then gravity is not strong enough to stop the expansion. The universe would expand forever. In this case, space-time would have a negative curvature, like the surface of a Pringles chip or a saddle. This is called an open universe. It is infinite in size. The third possibility is the borderline case. If the density of the universe is exactly equal to the critical value, then spacetime would be flat. In a flat universe, the rules of ordinary Euclidean geometry that you learned in school apply on the largest scales. Parallel lines stay parallel forever. The universe would expand forever, but the rate of expansion would slow down, approaching zero. A flat universe is also infinite in size. For decades, astronomers have been trying to measure the geometry of the universe. One of the best ways to do this is to look at the cosmic microwave background CMB. This is the faint afterglow of the Big Bang, a snapshot of the universe when it was only about 380,000 years old. At that time, the universe was filled with a hot, dense plasma. There were small fluctuations in the density of this plasma. These fluctuations are visible today as tiny temperature variations in the CMB. The apparent size of these fluctuations in the sky depends on the geometry of the universe. If the universe is flat, the light from these fluctuations travels to us in straight lines and they appear a certain size. If the universe is closed positively curved, it acts like a magnifying lens and the fluctuations would appear larger. If the universe is open negatively curved, it acts like a day magnifying lens, and the fluctuations would appear smaller. Our most precise measurements of the CMB from missions like the Wilkinson Microwave Anisotropy Probe MAP and the Planck satellite have measured the size of these fluctuations with incredible accuracy. The results are clear. To within a very small margin of error, the universe is flat. The total density of matter and energy in the universe appears to be exactly the critical density. This is a strange result. It's like balancing a pencil on its tip. Any small deviation from flatness in the early universe would have been magnified enormously over 13.8 billion years of expansion. The fact that it is so close to flat today implies that it must have been unbelievably flat at the beginning. This flatness problem is one of the puzzles that the theory of cosmic inflation was developed to solve. But the fact that we can even ask and answer a question about the shape of the entire cosmos is a direct result of the geometric view of gravity that Einstein gave us. Number 9. Relativity does not play well with others. Physics in the 20th century produced two monumental theories. One is general relativity, Einstein's theory of gravity and the cosmos. It describes the world of the very large planets, stars, galaxies, and the universe itself. The other is quantum mechanics. It describes the world of the very small atoms, electrons, and subatomic particles. Both theories have been fantastically successful in their own domains. They are the most tested and confirmed theories in the history of science. There's just one problem. They don't work together. The two theories are fundamentally incompatible. They are based on contradictory principles. General relativity is a classical theory. It describes a universe that is smooth, deterministic, and continuous. Space-time is a geometric fabric that bends and curves gracefully. And quantum mechanics, on the other hand, describes a universe that is lumpy, probabilistic, and uncertain. Energy, momentum, and other quantities come in discrete packets called quanta. At its heart is the uncertainty principle, which says that you can never know both the precise position and the precise momentum of a particle at the same time. The more you know about one, the less you know about the other. The quantum world is a world of probabilities, not certainties. This conflict isn't a problem for most of physics. In most situations, you only need one of the theories. If you're calculating the orbit of a planet, you use general relativity, and you can safely ignore quantum mechanics. The quantum effects are too small to matter. If you're studying the behavior of an electron in an atom, you use quantum mechanics, and you can ignore gravity. The gravitational force between them is trillions of times weaker than the electrical force. But there are situations where you need both. You need both to describe the singularity at the center of a black hole, where a huge amount of mass is crushed into a tiny space. You need both to describe the singularity at the beginning of the universe, the Big Bang, where the entire universe was smaller than an atom. In these extreme environments where gravity is incredibly strong and the scales are incredibly small, both theories should apply. But when you try to use them together, the equations break down, they produce nonsensical answers like infinite probabilities. This is the biggest unresolved problem in fundamental physics. The search for a single theory that can unite general relativity and quantum mechanics is the quest for a theory of everything, or more accurately, a theory of quantum gravity. Such a theory would describe all the fundamental forces of nature within a single framework. There are several leading candidates. String theory suggests that the fundamental constituents of the universe are not point-like particles, but tiny vibrating strings of energy. Different vibrations of these strings correspond to different particles. One of the vibrations corresponds to the graviton, the hypothetical quantum particle of gravity. Another approach is loop quantum gravity, which proposes that space-time itself is quantized. It's made of tiny, discrete loops or chunks of space and time. So far, none of these theories has been experimentally confirmed. They operate at energy scales that are far beyond the reach of our current particle accelerators. But the conflict between our two best theories of reality tells us that our understanding is incomplete. There is a deeper, more fundamental theory out there waiting to be discovered. Einstein himself spent the last 30 years of his life searching for a unified field theory, but he was unsuccessful. Today, thousands of physicists around the world are continuing that search. Number 8, the only thing that's constant is the speed of light. Before Einstein, our ideas about space and time were based on common sense. We assume that the speed you measure for an object depends on how you are moving. If you are standing on the side of the road and a car passes you at 50 miles per hour, you measure its speed as 50 mph. If you are in another car traveling in the same direction at 30 mph, you would measure the first car's speed as only 20 mph 50/30. If you were traveling towards it at 30 mph, you would measure its speed as 80 mph 50 plus 30. Speeds add and subtract. It seems obvious. This works perfectly for cars and baseballs. But in the late 19th century, physicists were struggling with light. A Scottish physicist named James Clerk Maxwell had developed a set of equations that described electricity, magnetism, and light. His equations predicted that the speed of light in a vacuum was a specific value about 300,000 kilometers per second. But the equations didn't say what this speed was relative to what was light traveling at this speed. The common assumption was that light must travel through a medium, an invisible substance that filled all of space. They called it the luminiferous ether. The speed of light would be constant relative to this ether. This meant that if the Earth was moving through the ether, we should be able to measure a change in the speed of light depending on which direction we measured it. In 1887, Albert Michelson and Edward Morley conducted a famous experiment to detect this ether wind. They used a very clever device called an interferometer to measure the speed of light in different directions. To their astonishment, they found no difference. The speed of light was the same in all directions, regardless of the Earth's motion. This result was a deep puzzle. It seemed to violate common sense. How could the speed of light be the same for all observers, no matter how they are moving? This is where the young Albert Einstein entered the picture. In 1905, in his special theory of relativity, he took a radical step. He abandoned the idea of the ether. Instead, he proposed two simple postulates. First, the laws of physics are the same for all observers in uniform motion. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. He took the strange result of the Michelson-Morley experiment and made it a fundamental principle of the universe. This simple idea has profound consequences. If the speed of light is constant for everyone, then something else must change to compensate. That something else is space and time. To keep the speed of light constant, measurements of distance and duration must be relative. They must depend on the observer's motion. This leads directly to the weird effects of time dilation and length contraction. It means that there is no absolute space and no absolute time. Everything is relative except for the speed of light. It is the one fixed, unchanging cornerstone of the universe. Number 7, two things happening at the same time is a matter of opinion. One of the strangest consequences of the constant speed of light is the relativity of simultaneity. This means that whether two events happen at the same time is not an absolute fact. It depends on who is looking. Two events that are simultaneous for one observer may happen at different times for another observer who is moving relative to the first. Well, Einstein explained this with a thought experiment. Imagine a long, fast-moving train. A person, let's call her Alice, is standing exactly in the middle of the train. Another person, Bob, is standing on the ground beside the tracks. Now, imagine that two bolts of lightning strike the train at the exact same moment. One hits the front of the train and one hits the back. Let's look at this from Bob's perspective, standing on the ground. The two lightning bolts strike simultaneously. The light from each strike travels towards Bob. Since Bob is standing still, and the strikes happened at the same time, the light from both events reaches his eyes at the exact same moment. For Bob, the events were clearly simultaneous. Now let's consider Alice's perspective inside the moving train. She is also standing in the middle. The two lightning bolts strike the train, but the train is moving forward. So, Alice is moving towards the point where the front bolt struck, and she is moving away from the point where the back bolt struck. The light from the front strike has a shorter distance to travel to reach her. The light from the back strike has a longer distance to travel. Therefore, the light from the front strike will reach Alice's eyes before the light from the back strike. From Alice's point of view, the two events were not simultaneous. She saw the front of the train get hit first, and then she saw the back of the train get hit. And since she knows she is in the middle of the train, and she knows the speed of light is constant, She can only conclude that the lightning must have actually struck the front of the train before it struck the back. So who is right, Alice or Bob? The answer from relativity is that they both are. Simultaneity is not absolute, it is relative to the observer's frame of reference. There is no universal now that everyone can agree on. My now is different from the now of someone flying past me in a spaceship. The difference is incredibly small in our everyday lives because we move so slowly compared to the speed of light. But it is a real physical effect. This idea shatters our intuitive understanding of time. We tend to think of time as a universal river that flows at the same rate for everyone. We think of the present moment as a thin slice that cuts across the entire universe. But relativity tells us that this is an illusion. Your now is personal. It's a slice of space-time that is tilted relative to mine. This means that questions like, "Hat is happening on Mars right now," don't have a single unambiguous answer. It depends on how you are moving. The very concept of a shared universal present moment is a casualty of Einstein's theory. Number 6, moving objects get squashed. If the speed of light is constant for everyone, then not only is time relative, but so is space. One of the direct consequences of special relativity is length contraction. This is the idea that an object in motion will be measured to be shorter in its direction of motion than it is when it is at rest. The faster it moves, the shorter it appears. This is not an optical illusion, it's a real physical effect related to the nature of space itself. Let's go back to the train. Imagine the train is 100 meters long when measured at rest in the station. Now, the train speeds by Bob, who is standing on the platform. If Bob could measure the length of the moving train, he would find that it is less than 100 meters long. From his perspective, the train has contracted or shrunk in the direction of its motion. The height and width of the train would be unchanged, only the length is affected. From the perspective of Alice, who is on the train, everything seems normal. The train is still 100 meters long. Her meter stick is still 1 meter long, but if she looks out the window at Bob on the platform, she would see the platform as being shorter than it was when the train was at rest. From her point of view, it is Bob and the platform that are moving, and therefore it is the platform that is contracted. Like time dilation, this effect is only noticeable at speeds close to the speed of light. At everyday speeds, the contraction is minuscule. A car traveling at 60 miles per hour is about 1 nanometer shorter than it is when parked, which is completely undetectable. But if a spaceship could travel at 87% of the speed of light, it would appear to be half its normal length to a stationary observer. If it could reach 99.5% of the speed of light, it would be only 10% of its normal length. As an object approaches the speed of light, its length in the direction of motion approaches zero. This might seem impossible to believe, but it has been indirectly confirmed by experiments. For example, consider particles called muons. They are created high in the Earth's atmosphere when cosmic rays strike air molecules. Muons are unstable and decay very quickly. Their average lifetime at rest is only 2.2 microseconds. And even traveling at nearly the speed of light, they should only be able to travel about 660 meters before they decay. But we detect large numbers of them on the surface of the Earth after they have traveled through about 10 kilometers of atmosphere. How is this possible? The answer involves both time dilation and length contraction. From our perspective on Earth, the muon's internal clock is ticking very slowly because it is moving so fast. This allows it to survive the long journey. From the muon's perspective, its lifetime is still 2.2 microseconds. But the atmosphere is moving towards it at nearly the speed of light, therefore the distance it has to travel is length contracted. From the muon's point of view, the 10 kilometers of atmosphere is squashed down to only a few hundred meters, a distance it can easily cross before it decays. Both perspectives give the same correct result. the muon reaches the ground. This shows how time dilation and length contraction are two sides of the same coin, two necessary consequences of a universe where the speed of light is the ultimate constant. Number 5, time moves slower when you move faster. One of the most famous and mind-bending consequences of special relativity is time dilation. It's the idea that time can pass at different rates for different people. Specifically, a clock that is moving relative to an observer will be measured to tick more slowly than a clock that is at rest with the observer. The faster you move, the slower time passes for you, relative to someone who is stationary. This isn't a mechanical issue with the clocks. It's not that motion somehow damages the clock's mechanism. The effect applies to all clocks, whether they are mechanical, digital, or even biological. Your own heart rate, your metabolism, your aging process, they all slow down when you are in motion. From your own perspective, time would always feel normal. A minute would still feel like a minute. But to someone watching you fly by at high speed, it would look like you were living in slow motion. This comes directly from Einstein's second postulate, that the speed of light is the same for everyone. He imagined a light clock. It consists of two mirrors with a beam of light bouncing back and forth between them. Each time the light hits a mirror, the clock ticks. Now, imagine this clock is stationary. The light just travels straight up and down, but if the clock is moving from the perspective of a stationary observer, the light has to travel on a diagonal path to keep up with the moving mirrors. This diagonal path is longer than the straight up and down path, since the speed of light is constant and the light has to travel a longer distance. It must take more time to make each tick. Therefore, the moving clock runs slow. Like length contraction, this effect is completely negligible at the speeds we experience in our daily lives. But it becomes very significant at speeds approaching the speed of light. If you were to travel in a spaceship at 99% of the speed of light, for every 1 year that passed for you, about 7 years would have passed on Earth. If you could reach 99.99% of the speed of light, over 70 years would pass on Earth for every one of your years. This isn't just a theoretical concept, it's a measurable reality. Time dilation is constantly being confirmed in particle accelerators. Unstable particles moving at near the speed of light are observed to live much longer than they do when at rest, exactly as the theory predicts. It's also a crucial factor in the operation of the GPS system. The satellites are moving at about 14,000 kilometers per hour. This speed causes their onboard atomic clocks to run slightly slower than clocks on the ground by about 7 microseconds per day. If this relativistic effect were not accounted for, the entire GPS system would fail within minutes, producing navigational errors that would grow by about 10 kilometers every day. So every time you use your phone's map to find your way, you are relying on the reality of time dilation. Time is not a rigid universal metronome. It is a flexible personal quantity that depends on how you move through the universe. Number 4, a space trip could make you younger than your twin. The idea of time dilation leads to a famous thought experiment known as the twin paradox. It's designed to highlight the counterintuitive nature of relativistic time. Imagine a pair of twins, both 20 years old. One twin, the traveler, gets into a spaceship and flies to a distant star at a very high speed, say 99.5% of the speed of light. The other twin, the stay-at-home, remains on Earth. The traveler goes to a star that is 5 light-years away. From the perspective of the stay-at-home twin on Earth, the journey out will take a little over 5 years, and the journey back will take a little over 5 years. So, the total trip time for the traveler will be about 10 years. When the traveler returns, the stay-at-home twin will have aged 10 years and will now be 30 years old. But what about the traveler? Because she is moving at such high speed, her time is dilated. It is passing more slowly relative to Earth time. At 99.5% of the speed of light, the time dilation factor is about 10. This means that for every 10 years that pass on Earth, only 1 year passes for the traveler. So during the 10-year round trip as measured from Earth, the traveler will have aged only 1 year. When she steps out of her spaceship, she will be 21 years old. Her twin brother, who stayed on Earth, will be 30. The traveler is now 9 years younger than her own twin. This is where the paradox comes in. From the traveler's point of view, she was the one who was stationary inside her ship, and it was the Earth that was moving away from her and then back towards her. So shouldn't she see the Earth's clocks as running slow? Shouldn't she expect her twin on Earth to be younger when she returns? Why is there a difference? Who is actually younger? The resolution to the paradox lies in the fact that the twin situations are not symmetrical. The stay-at-home twin is in a single, consistent, inertial frame of reference the whole time. An inertial frame is one that is not accelerating. The traveler twin, however, is not. She has to accelerate to get up to speed. She has to decelerate to stop at the distant star. She has to turn around and accelerate again to come home. And she has to decelerate to land back on Earth. This acceleration is what breaks the symmetry. It is the traveler who has undergone the change in motion, not the stay-at-home. Therefore, it is the traveler who experiences less elapsed time. There is no paradox. It is a real physical effect. If this experiment could be carried out, the traveler would genuinely be younger. While we can't send humans on such a trip yet, we have performed equivalent experiments. In 1971, physicists Joseph Hafele and Richard Keating flew highly accurate atomic clocks on commercial airliners around the world. They flew them both eastward and westward. They then compared the time on these clocks with a master clock that had remained on the ground. The flying clocks were out of sync with the ground clock. The amount of the time difference, although only a few hundred nanoseconds, matched the predictions of relativity perfectly, taking into account both the effects of special relativity due to their speed and general relativity due to the difference in gravity at altitude. The twin paradox is not a paradox, it's just how the universe works. Number 3. Mass is a form of frozen energy. E equal mc squared. It is the most famous equation in all of science. Even people who know nothing about physics can recognize it. But what does it actually mean? It means that energy equals mass times the speed of light squared. But that's just the formula. The idea behind it is one of the most profound in history. It says that mass and energy are the same thing. They are two different forms of the same fundamental stuff. Mass is a highly concentrated frozen form of energy. The c in the equation is the speed of light. This is a huge number, about 300 million meters per second. The squared is that number multiplied by itself, which is an absolutely enormous number. What the equation tells us is that a tiny amount of mass can be converted into a tremendous amount of energy. The amount of energy locked up in the mass of a single paperclip is enough to power a major city for a day. This idea was a direct consequence of Einstein's 1905 paper on special relativity. He realized that as you accelerate an object, its mass effectively increases. It gets harder and harder to push. As it approaches the speed of light, its mass approaches infinity, which is why nothing with mass can ever reach the speed of light. This increase in mass comes from the energy of motion kinetic energy being converted into mass. He then generalized this to say that all energy has mass and all mass has energy. This principle explains where the energy of the sun and other stars comes from. Stars are not burning in the chemical sense, like a log in a fire. They are giant nuclear fusion reactors. In the core of the sun, under immense pressure and temperature, hydrogen nuclei are fused together to form helium nuclei. The key is that a helium nucleus has slightly less mass than the 4 hydrogen nuclei that went into making it. A small amount of mass, about 0.7% of the original mass, disappears in the process. This missing mass is not really gone. It has been converted directly into energy according to E equals mc squared. This energy is what makes the sun shine and provides the light and heat that makes life on Earth possible. Every second, the sun converts about 4 million tons of its mass into pure energy. The equation also works the other way around. Energy can be converted into mass. In high-energy particle accelerators, physicists can smash particles together at nearly the speed of light. The huge amount of kinetic energy in the collision can be converted into new particles with mass, particles that didn't exist before the collision. This is how many new subatomic particles have been discovered, and of course, the equation is the basis for nuclear power and nuclear weapons. In a nuclear reactor, heavy atomic nuclei like uranium are split apart in a process called fission. The resulting pieces have slightly less total mass than the original nucleus. This lost mass is converted into a huge amount of energy, which is used to generate electricity. The equation E equal SMC squared is not just an abstract formula, it describes a fundamental truth about the universe. It is the reason stars shine, the source of immense power, and a direct window into the deep unity of the physical world. Number 2, space and time are a single fabric. Before Einstein, we thought of space and time as two completely separate things. Space was the three-dimensional stage where the drama of the universe played out. It was described by length, width, and height. Time was a separate, one-dimensional thing, a universal clock that ticked away at the same rate for everyone, everywhere. It was the background rhythm of the universe, one of the most profound shifts in thinking that came from relativity was the idea that space and time are not separate. They are inextricably linked together. They form a single, four-dimensional continuum called spacetime. This wasn't just a clever way of talking about things, it was a new mathematical and physical reality. An event in the universe is no longer described by just its 3 spatial coordinates. It needs 4 coordinates to be fully specified, its location in space x, y, z, and its location in time t. This idea was first formalized by one of Einstein's former teachers, Hermann Minkowski, in 1908. He famously said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Einstein was initially resistant to this 4-dimensional geometric interpretation, but he soon embraced it as the natural language for his theory. It became the foundation for his development of general relativity. In the framework of space-time, the strange effects of special relativity, like time dilation and length contraction, start to make more sense. They are not two separate phenomena. They are consequences of the fact that different observers are just slicing up the same 4-dimensional space-time in different ways. Moving through space is linked to moving through time. Everyone is always traveling through space-time at a constant speed, the speed of light. This sounds strange because we know we don't move through space at the speed of light. But think of your motion as a vector in 4-dimensional space-time. This vector has a constant length for everyone, and that length is the speed of light. If you are at rest in space, then all of your motion is through the time dimension. You are traveling through time at the maximum possible rate. But if you start moving through space, some of your motion has to be diverted from the time dimension into the space dimensions. To keep the total length of your space-time motion vector constant, your speed through time must decrease. This is time dilation. The faster you move through space, the slower you move through time. If you could travel through space at the speed of light, which only massless particles can do, all of your motion would be through space, and you would have no motion left for the time dimension. For a photon of light, time does not pass at all. From its perspective, its journey from a distant star to your eye is instantaneous. This unification of space and time into a single entity was a revolution. In general relativity, Einstein took it a step further. He showed that this space-time fabric was not flat and rigid. It was dynamic. It could be bent, stretched, and warped by the presence of matter and energy. And this curvature of space-time is what we experience as gravity. The concept of space-time is not just an abstract mathematical tool. It is the very stage on which the universe exists, a dynamic and active participant in the cosmic dance. Number one, your phone knows where you are because of relativity. Every day, millions of people use the Global Positioning System, or GPS. It's in our cars, in our phones, and in our watches. We use it to navigate to a new restaurant, to track our morning run, or to find our way out of the woods. We take it for granted. But the GPS network is a stunning feat of engineering that relies completely on Einstein's theory of relativity. If the system didn't account for relativity, it would fail catastrophically within minutes. The GPS system consists of a constellation of about 31 satellites orbiting the Earth at an altitude of about 20,200 kilometers. Each satellite carries a highly precise atomic clock. To determine your position, your GPS receiver on the ground needs to pick up signals from at least 4 of these satellites. The receiver calculates its distance from each satellite by measuring the time it took for the signal to travel from the satellite to the receiver. Once it has the distances from 4 satellites, it can pinpoint your location on Earth through a process called trilateration. The whole system depends on incredibly accurate timing. The signals travel at the speed of light. If the timing is off by even a tiny fraction of a second, the calculated position will be wrong by a large amount. This is where relativity comes in. And it's not just one, but both parts of Einstein's theory that are essential. First, there's special relativity. The GPS satellites are moving at a speed of about 14,000 kilometers per hour relative to the Earth's surface. According to special relativity's principle of time dilation, this high speed causes the atomic clocks on the satellites to tick more slowly than clocks on the ground. The effect is small but measurable. The satellite clocks lose about 7 microseconds millionths of a second every day compared to clocks on Earth. Second, there's general relativity. The satellites are in a much weaker gravitational field than we are on the surface of the Earth. According to general relativity's principle of gravitational time dilation, clocks in a weaker gravitational field tick faster. This effect is even larger than the effect from special relativity. The clocks on the satellites gain about 45 microseconds every day compared to ground-based clocks. So, we have 2 competing relativistic effects. The satellites' clocks are slowed down by their speed, but they are sped up by the weaker gravity. To get the total effect, we have to combine them. The speeding up effect from general relativity is stronger than the slowing down effect from special relativity. The net result is that the clocks on the GPS satellites run faster than clocks on Earth by about 38 microseconds per day. 45/7 equals 38. This may not sound like much, but if the engineers who designed the GPS system had ignored it, the system would be useless. A timing error of 38 microseconds per day would translate into a navigational position error that would grow at a rate of about 10 kilometers every single day. Within a few minutes of turning the system on, it would tell you that you were in the next town over. To counteract this, the atomic clocks on the satellites are deliberately engineered to run slightly slower in the factory before they are launched into space. They are set to tick at a rate of 10.22999999543 megahertz, instead of the standard 10.23 megahertz. Once they are in orbit, the combined effects of relativity cause them to tick at the correct rate, perfectly synchronized with the clocks on the ground. So, every time you use a GPS device, you are using a real-world application of Einstein's century-old theories about the nature of space, time, and gravity. Without his insights, our modern world of instant navigation would not be possible.